Hello, I'm Michael O'Connell, and in today's video, we're going to examine a situation in which we have a cup of liquid at rest on a turntable. So I'm going to draw that situation on the board here. So we have our liquid at rest. And what we're going to do is see how fast we can spin that turntable such that the liquid in our cup doesn't spill out of the cup. So if you've ever had liquid in a cup and you've spun it around, you get a very interesting profile for this liquid surface. It looks kind of like a parabola. I'm going to draw a larger dip here, okay? Because this is our original height. Let's call that H naught. So that's the initial fluid level in our cup of liquid. And then I'm also going to specify with a capital H the height of our cup. Why would I do that? Well, again, we're rotating this turntable at some angular velocity. And that maximum velocity at which we're able to spin the turntable is going to, without spilling the liquid, of course, is going to be limited by the height of our cup. If I have a cup that's taller, I'm going to be able to spin my turntable a lot faster without spilling any of the liquid inside. Okay? So that's important to recognize. So what's causing this change? That's what we have to first ask ourselves. And this is going to be a repeat of what we've done in many of the videos so far, in which we're going to use the basic equation for static fluids. So that describes the differential change in pressure over the differential change in position. And we say that that's equal to the density of our fluid multiplied by its acceleration. I want to talk about this acceleration, especially in the case of our turntable, right? So we're spinning this in a circle. So hopefully we remember that that acceleration vector in a circle is always pointing towards the center, right? So that would actually be the wall, right, of our container that has that acceleration vector towards the center, pushing the contents, keeping them from, flying off in some tangential path off of the turntable, right? That's what the walls of the container are doing. But we have to consider the acceleration of the fluid, right? So from the perspective of the fluid, that acceleration vector is actually outwards, right? This is where I would ask you, if you're considering the acceleration due to gravity on Earth, are you accelerating to the Earth, or is the Earth coming to meet you? So it's all a matter of perspective, is my point there. So that's why it's important to realize that with respect to our fluid, which is what this basic equation of static fluids is describing, that acceleration, that radial acceleration, is actually outwards. So what do we do next here? I think what I would ask is, well, what is this acceleration, right? And we do have a formula for that. So the centripetal acceleration is the radius of our circular path multiplied by the angular velocity squared. There is a way to derive that using angular coordinates. So if we're interested, I can do that. Basically, I feel bad because you do have to erase stuff here, which I think I'm okay doing because I do think that this is worth demonstrating. We have our circular path. We have some radius r. We know that we can describe these rectangular coordinates, right? We've hopefully seen this. So x would be r cosine theta with respect to some starting line, right? Okay, and then y is r sine theta. What would theta be? Here I would ask you to consider if I run in a straight line, so I have some displacement, x, let's say. To find that displacement, you would say, well, okay, how fast did you run, assuming I ran at a constant rate, velocity, multiplied by time, right? How long did you run? So that is what we are going to apply to this situation here for our theta, right? So it'd be the angular velocity instead this time. This displacement here, it's angular, okay? So that'd be theta. And then we would have the angular velocity there. So that substitutes into both of these. Okay. All right, I think we're ready to take some derivatives, right? So if we want to find the velocity here, we would take the derivative with respect to time, okay? So what is that going to be? Well, this is going to come out, and then this is going to be negative. So negative r omega, and then sine wt. dy dt is similar, right? And if you're a few steps ahead of me, and you know that we're going for acceleration, you really would be taking the second derivative of both of these. And hopefully you remember kind of a quick trick for that would be you could actually pull out this omega and square it because you're doing the second derivative, right? Chain rule twice. And then when you have a trig function like this, like cosine or sine, this is an easy thing that I remembered in calculus, was you take the opposite of it and you square it. So both of these are going to be, so like you would take the derivative of the velocity in the x direction, right, with respect to time. That would be your acceleration in the x direction, right? And so based on what I have just stated, what would that be? Well, that's going to be negative r omega squared cosine squared omega t, okay? And so it'd be the same idea for the acceleration in the y direction. So we have an acceleration component in the y direction and an acceleration component in the x direction. So this is just vector resolution at this point. So our centripetal acceleration is going to be involved. Wow, that is not very dark, so we need to look out for that. But it is visible. It's a little bit blurry. But these are going to go in there. Now what happens here? We know this, right? And we also know that these negatives, we don't have to worry about those because what I forgot to show here is that these are squared. Okay? But cosine squared plus sine squared can be factored out. We know that identity to be 1. So what would we end up getting here, right? Well, let's see what you would have here. So you'd have r squared omega to the 4th. And then that, again, that would be the one that's factored out with blah, 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 right? So yeah, I kind of, I guess, stated that perhaps incorrectly. But again, you have these terms. It's really this term that you factored out. You take the square root of that, and you get your centripetal acceleration. So if you didn't like that, you can just skip ahead, I suppose. But that's how we get the centripetal acceleration. And like I said, so for our liquid contents, that's going to be outwards. Now, why is that important? Well, when we're looking at this situation, the next term we need to look at, so we have our basic equation of statics, is what is our position? Well, we have this cup, right? It's like a cylinder with some radius. So that's how the pressure is changing. It's changing radially. It's changing with respect to the radial position. Okay? And as you'll see, we can actually also find the pressure going vertically. This would be horizontally, right? And that's actually going to be super important for us. The thing I would say there is just remember that pressure is associated with a certain point in the fluid, and that will be extremely helpful for us when we try to get an equation for the height, or really I should say the depth, from this lowest point, the dip that we see when we spin our cup, right? Or in this case, when we spin that turntable, we want this height. We'll be able to get two expressions for pressure, one from the vertical, one from the horizontal, that are equal to get that expression for this height h. But we're not there quite yet, right? So we have the density of the fluid, and then we have the centripetal acceleration here. Okay? So what do we do here? Well, we need an equation for pressure. We need to figure out how pressure is changing with respect to our position in our fluid. Okay? So we just do some basic integration. So we can integrate both sides. We have to move the dr over, obviously. And then these two terms come out of the integral. So we would have this expression here. So hopefully you followed me through that. And what do we do here? Well, now we have some new pressure. These P sub 1, R sub 1, so this would be the pressure at some known radial position. And I'll clue you in again, looking ahead at the profile of our liquid, we want to take that at the lowest point. And you'll see why as we continue. But we can also assume that we have air right out here. Okay? And we can measure or determine the pressure at points in our fluid relative to that. So we can take the pressure at the surface of our liquid here, right, to be constant. We can take it as 0, which will make things much easier for us. Okay? And you'll see that as well. So this would be the difference between P and P sub 1. Okay, we have the density times the angular velocity squared. And then we have these as well. So this would be 1/2 times R minus R1 squared. Okay. So if you're following along, write down this equation because that one will be super important. Fortunately, as I said, and we can actually just do this now to make the transition much easier, we're going to look back at our spinning cup of liquid. Okay? Yes. Just making sure that that is visible. You can give a little more room here on the bottom, probably. Okay? And we're going to start in the middle. So one nice thing about that is what would R1 be, right? What would our known radius be? This is 0. And then, as I said before, at the surface, this pressure there is gone. Okay? So you might be wondering, okay, that's really cool, right? So now we would have this expression for the pressure. So where do we go from there, right? Okay. So basically, we still had that R term, right? So I need to pick a point, right? Well, we want to go some arbitrary distance horizontally, maybe over to here, right? So this is some distance R. And then now we have a new pressure associated with this point in our liquid. But this is where something really neat comes in, I think, is that, again, that pressure is associated with this point, but we also have liquid above it. This isn't at the surface, obviously, because then by our convention in this problem, we would have taken that to be P0, right? But we have this here, right? Some change in height. And we know that expression, right? So that pressure would be the density of our fluid multiplied by the acceleration. That would be g, gravity. So we can take that by convention downwards to be positive, right? And then the change in depth, h, we could say, in this case. Okay, so there's one thing that I forgot to address here, right? And hopefully you're able to see why it will make sense. I took our basic equation of statics, right, where we had on the right-hand side density times the acceleration. In this case, it would have been the centripetal acceleration because we were analyzing how the pressure changes with respect to radial position. But hopefully you see in this equation, as we increase this radius r, right, as we go out from this center point that I've selected, our lowest point with the dip in our liquid profile, this pressure increases, right? Okay, it's some value. But as I said, that acceleration of our fluid would be outwards as we're moving it around the turntable. So it's in the same direction, right? So that's why that is positive, okay? So that is a small little point that I just forgot to explain, but it is still relevant. So what are we going to do next? Well, as I just showed there, and I'm going to be redrawing it soon, I'm sure, these pressures are the same, right? Because they're associated with that point in the fluid. Okay. So what does that mean for us? Oh, and a term I forgot, right? This is, you have the r squared. Okay, so our densities are gone, right? And then we just divide by g, and we get this expression where the height is the angular velocity squared multiplied by our radial position squared from the center, okay? Divided by 2 times the acceleration due to gravity. Okay, so this is another important equation. Because basically what we're going to do, we want to describe how this, so remember what this height is. That's what I would say here. That's like so important. Okay, remember this is our initial fluid level, those dashed lines I have. So we have some depression here that we'll call D. But then what we just did here, where we moved over some radial position R, and then we moved down some depth in the fluid H, that's what this height describes. Okay, well that's relevant for us, right? Because as we increase our radial position, as we move outward, this depth of our fluid to such point increases. So if we keep moving out and out and out, we're going to get to this point, right? Okay, and this is where if you spin that turntable too fast, you're going to have liquid that's spilling out of there. Okay, so this expression is extremely important, and as I said, so critical in the beginning of the video, that we're limited by that large h. We're limited by the height of our cup that's holding the liquid. Okay, so what we want to describe specifically is how the height, or this fluid depth over here, based on that liquid profile, we want to model how that changes with respect to our radial position, and also very importantly, the angular velocity at which we're spinning our turntable. So that's crucial. And we're going to want to do the same thing with our depth here. Okay, so how might we do that? This part has a little bit more to it, right? So I've drawn our initial and final situations here. We can add some other relevant variables here, like our large h. This is our initial fluid level, h naught. And here, we just have to make a very important observation, right? So we have some depression, right, that creates our profile of the liquid surface, right, after we spin the turntable. So here, we want to balance our volumes, actually. And I think this is actually, I think it's fairly intuitive, right? So if we draw another dashed line, so this is where the lowest point, right, from that depression is going to be. I'm drawing that on the initial situation as well. Okay, so this volume here, it gets kind of moved around, right, once we spin that turntable. So you have this volume there and that volume there, and then your lowest point. This fluid, where did it come from? All of it came from here, okay? And that is basically going to be that's going to be the means by which we find an expression for this depression on the liquid surface, okay? So what would this be? Here I would like us to be able to like visualize we're looking on top of our cup here, okay? Right? Okay, so it's some sort of circle. So we want the volume, right? So we have some surface area of the circle. That's pi. I'm going to denote this with big R, large R squared. So that is the total, that's like the total radius, okay, of our cup is large R. And that will be important for us. And then what's our depth? Well, our depth is just how much we went down, which is going to be that depression that occurs, okay? So that's going to be important. And then this has to be equal to these volumes, right? Okay, so how can we model those volumes? This is where some good old calculus comes in, okay? So here, we're going to need some integration, right? Because we have a changing radial position, right? Because basically, in this case, right, at all the positions, we have the same the same height in fluid, right? So we can actually calculate exactly, without any integration or anything like that, what our fluid volume or our liquid volume is. In this case, we don't have that luxury, right? Okay, so we can look at the top view once again, right? And let's just take a small section, right, for our radial position, like just a very, very small change all the way around, okay? So how would we model this, right? So as you can see, we can take that height h that we had before, right? If we're taking this at some position here, you know, and again, it would go all the way around, so you would see it there as well, okay? Does that make sense? We're looking from the top view, okay? So this is a differential change in the radial position, okay? When we're looking at this spinning cup of liquid from the top view, okay? So we need the perimeter, right? And then we can multiply it by that thickness to get the differential area, right? So the differential area here would be 2 pi r, our circumference, multiplied by dr. So what do we need now? Well, we just need h, right? We need to multiply that by h, and then now we have that change in volume. But again, yeah, this is a differential. It's not like this constant volume there that we had at the start before we spun that turntable, okay? You're probably going to see me do this, like spun that turntable. I've probably done that like 12 times in this video. So, yeah, that is something that you can either get a lot of enjoyment out of or be extremely annoyed by. So hopefully you're not too annoyed by it. Okay, what is going to be our bounds of integration, right? That's kind of what we would need to think of. Remember that big R I talked about? That's going to be important for us, right? So we're going to measure this with respect to the total radial position that we can cover, right? So at some point 0 in the center, and then if we're going all the way around, we have to extend that to some radius r, and that's that large r portion, right? Okay? So let's set these equal to each other, right? This was the initial, and then now we're integrating. Now, oh, whoops. This is where we need to be a little careful, right? So let's just keep everything inside the integral, and then we'll talk about it. Okay. This is where it gets a little easy to make mistakes if you forget to make a substitution, or you just get stuck, which isn't good either. Okay? So we understand that that's where we're integrating, right? Because again, we have that dr, that differential change in the radial position. So we have our height. Okay, this is what you needed to remember to substitute. So that drops in there. And that's important because that has a radius, right? That height or that depth within our fluid depended on our radial position, which is like, obviously, if you go closer to that wall, that's where your fluid's much higher. Okay, so we plug that in. 2 pi is constant. Okay, and now you see, with this h that comes in there, those are going to cancel, right? Those 2's. Okay, so hopefully you see that. These pi's cancel as well. So we have a pretty good situation here, don't we? This is the angular velocity, so that comes out of the integral. G would obviously stay out. And then you have this, r squared, multiplied against this r. Wow, this is not too bad at all. So we have r squared d, omega squared over g, this integral here, and then we have r cubed, because it's r times r squared, dr. Okay, so I hope that's, yeah, actually that's pretty visible there. I've drawn it pretty big and obnoxiously. Okay, so this is 0, so we don't have to worry about that. We just do have to worry about the large r. So integrate that, that would be 1/4, right? Bring the 3 plus 1 down, and then add the 1 up there, okay? So what would that be? That's going to be r to the 4th power over 4. Awesome. R squareds cancel. Okay, so this becomes r squared. And with that, that's your expression. So let me, I'm a little weary to just erase this, but I'm going to risk it. So this is our depression that we've modeled now, and that's dependent on the angular velocity squared the radius of our actual cup squared over 4 times the acceleration due to gravity. Okay, now we are officially in the home stretch here. This is great because we have an expression for the depression as it changes with the angular velocity at which we spin our turntable. And then we also have an expression for the depth within our fluid, like to a certain point. Okay, and then how that changes with radial position, obviously, and the angular velocity, of course, which is what we're after. So what do we do next, right? This is where the limiting factor, the ultimate limiting factor, the height of our cup comes into play, okay? So I'm going to redraw the situation that we've had one more time. Before I do that, I'm going to write my expressions here so that we just don't forget them, okay? So we have that expression and that expression. Okay. So in our initial situation, we have that and then this, drawing them kind of skinny. And then we have this. Okay. Let's think about this here, right? Do some dashed lines. Okay. So we know that this initial fluid level we said was h naught. The height is h, okay, of our cup. So hopefully, again, trying to make sure that that's visible. This is our depression, d. And then we have some height, h, right? Okay. So how do we do this, right? Well, we can clearly see, actually, that this h naught minus our depression is going to account for all the height here, right? Okay, that's good. So if you don't mind, I'm going to wipe these away now because we've expressed this portion of the height. So what else do we have left to get some expression that's equal to the big H, right? To the height of our fluid. Well, fortunately, we have this changing height, h. Uh-oh, lights just went out. So I'm going to do this because it'll be fun. It's back. That's cool. I love the clapping and the light turning on. That's amazing. Okay. So as we move out with our radial position, right, this height increases. So if we move all the way out to big R, right, the full radius of our cup, this is going to be all the way up here. And what do you know? We've accounted for all the height once we do that. So that means this large R, that needs to go into this expression for our height, h. Okay? And if we do that, then that means that this h plus this expression, the difference between our initial fluid level and the amount of depression that we saw to the lowest point on our liquid profile, that plus this, now, with the large radius, that's going to be equivalent to our height. Okay, so let's express that in some equation. So quite simply, we can express that as the height of our cup is equal to the initial fluid level that we had, subtracted from the depression, added to that additional height that we need, h, to get to the top, to figure out the maximum angular velocity of which we can spin the turntable and get away without spilling it. Okay. So what do we do here? Well, we just plug in our terms, right? So here we're going to have omega squared large R squared over 4g that's for d, okay? And then plus omega squared big R squared 2g. Oh, this is great, right? Because look at those terms. All of those are the same. So what's 1/2? What's 1/2 plus negative 1/4? It's positive 1/4, okay? So that's excellent. So we have a really, really good expression here. We have large h minus, I'm moving this term to the other side, our initial fluid height. So that difference can be expressed with the angular velocity at which we spin our turntable, squared, multiplied by the radius of our cup squared, and then divided by 2 times the acceleration due to gravity. And what do we do from here? This is just algebra time now, because now that we plugged in the radius of our cup into this expression for the depth in our fluid to some point that depended on radial position. Now that we've done that, this omega that we're solving for, this final expression, this is the end of the video, right? This is the maximum angular velocity that we can spin our turntable without any of that liquid, or, just barely without any of that liquid spilling out of our cup. So that's really cool. We multiply both sides by 2g and then divide by r squared and take the square root. So you have 2g large H minus H naught over r squared. And I made a mistake here, obviously. I forgot. This is 4g, right? Positive 1/2 minus 1/4 is positive 1/4. So that was 4g. And I think that's why when I solved this on my own, I wanted to be fancy, I guess you could call it if you're that way, and bring the 2 out of the radical and just have g times h minus h naught over r. So that comes out of the radical as well. So this expression describes the maximum angular velocity that you can spin that turntable and no liquid will spill out of your cup. I promise. Okay? So I think this was a really cool video. Hopefully you enjoyed it. I thought it was really cool that you could figure out how fast you could spin a turntable without any liquid spilling. It makes me tempted if I had the time to try it at home, but maybe you do have that time and you're able to do that. I hope this video was helpful, and I hope you were able to see, in spite of some of the issues with the marker, because I know the camera quality and all of that isn't great. So thank you so much for watching, and I'll see you next time.